It's not always clear if a concept in your domain model is an entity or a value object, and unfortunately there are no objective attributes you could use to get to know it. Whether or not a notion is a value object fully depends on the problem domain. A concept can be an entity in one domain model and a value object in another. For example, in our system, the money class is certainly a value object. At the same time, if you build a software for tracking the flow of the cash in the whole country, you do need to treat every single bill separately, as you need to gather statistics for each of them. In this case, the notion of money would be an entity, although you would probably name it a note or bill. Despite the lack of objective traits, you can still employ some techniques in order to attribute a concept to either entities or value objects. First of all, you should take into account the notion of identity we discussed previously. If you can safely replace an instance of a class with another one, which has the same set of attributes, that's a good sign this concept is a value object. A good way of thinking of value objects is comparing them to integers. Do you really care if the integer 5 is the same 5 that you used in the previous function? Definitely not. All 5s in your application are the same regardless of how they were instantiated. That makes an integer essentially a value object. Now ask yourself, is this notion in your domain looks like integer? If the answer is yes, then it's a value object. In our application, we don't really care where the instances of the money class come from, and they are really similar to integers because of that. All said above has an important implication. Always prefer value objects to entities. Value objects are immutable and more lightweight than entities. Because of that, they are extremely easy to work with. Ideally, you should always try to put most of the business logic into value objects. Entities in this situation would act as wrappers upon them and provide more high-level instructions. Also, it might be that a concept you saw as an entity at first, essentially as a value object. For example, an address class in your system could be introduced as an entity initially. It may have its own ID field and a separate table in the database. But after revisiting it, you might notice that in your domain, addresses don't actually have their own identity and can be used interchangeably. In this case, don't hesitate to refactor your domain model and convert the entity into a value object. A typical application contains a lot of entities, so there should be a base class where you can gather common behavior for each of them. Let's discuss different approaches for creating such a base class. The first option we have here is to introduce an interface like this. That way, we would be sure all domain entities in our model have some minimum functionality, the ID property. Although it might seem a good decision, in most cases having an interface as a base entity is a bad idea. First of all, interfaces don't allow you to gather any logic in them. You need to implement this logic yourself, which leads to a massive code duplication. Even in this example, you need to create the ID property in every single entity, which is a heavy violation of the "don't repeat yourself" principle. Secondly, the use of an interface doesn't show the appropriate relationship between domain entities. Implementing an interface means that your class makes a promise to have some functionality defined in the interface. Two classes implementing the same interface don't tell us anything about their relationship. They can be related, but it also can be that they belong to entirely unconnected hierarchies. In other words, the iEntity interface introduces a can-do relationship, whereas domain entities should be connected to the base class by is-a relation. Not only such classes should have common functionality, but they themselves are entities. The only way for us to avoid these drawbacks is to introduce an abstract base class. Here is the actual code for the entity base class. You can see it contains an identifier and equality operators. Let's walk through it together. As we discussed earlier, entities have their own inherent identity. The best way to represent this identity is to introduce a separate member, the ID property. It's a good idea to use a long type for this purpose by default, as such IDs are easier to work with than, say, GUIDs. The equality members consist of 4 methods. The equals method is defined in the base object class and is often used by .NET internally. For example, when we call the contains method on a list of entities, .NET base class library compares the objects inside the list with the target one by calling the equals method. The default equals implementation gives us only reference equality. As we discussed earlier, entities also possess the identifier equality, so we need to override this method in order to introduce it. Here's how it looks like inside. We try to cast the other object to entity, compare the two references to each other, that gives us the reference equality. If the type of the entities is not the same, they cannot be equal no matter what IDs they have. Also, if any of the identifiers is 0, it means that the ID was not yet set to the entity, and we cannot compare it to other entities because its identity is not yet established. And finally, if all previous checks are passed, we compare the identifiers themselves, which gives us identifier equality. Aside from the equals method, it's also a good idea to define the equality operator, so that we can use it in our code like this. The only difference between the equality operator and the equals method is that the former can accept nulls for both operands, hence these checks here. You can see if both of the parameters are null, we return true. After that, we can call the equals method we implemented earlier. The inequality operator is very simple, it just calls the equality operator and reverts the result. Finally, we also need to implement the getHashCode method. It's important for two objects which are equal to each other to always generate the same hash code. Here, the hash code depends on the object's type and identifier, which are the parts of the object's identity. If you want to learn more about this method, check out this great Stack Overflow answer. Some developers also implement the IEquatable interface on the entity class like this. You can see that the equals method just converts the object parameter to the entity type and calls the new method. I tend not to do that because this interface was designed for the use in value types, structs in other words, and doesn't provide any additional value in classes. Therefore, its usage here violates the Yagni principle. You might have noticed that we don't set the ID property anywhere in this class. We will talk about it when we'll be discussing persistence for our domain model in the context of object relational mappers. Now, as we have the entity-based class, we can inherit our snack machine from it. This is our first fully fledged entity. In this demo, you saw the entity-based class we'll be using in our application. It's important to remember that, unlike value objects, each entity has their own identity. The best way to introduce this identity is to put it into the base class. The additional benefit here is that we are able to implement all required equality members in a single place. All entities in our domain model get them for free just by inheriting from the base class. Value objects don't have their own identity, and thus they shouldn't have the ID property like entities. It also means that we cannot place all code required for equality in a base class. In order to implement structural equality, we need to know the internals of each value object class. Nevertheless, we can still gather some logic common to such classes. Here's the code of the value object base class. You can see that we do override the equals method, but delegate the actual work to the abstract equals core method. And the same is for getHashCode. We could just leave the equals and getHashCode methods without overriding them here, but this practice has two advantages. First, the new two methods are abstract, meaning that we won't forget to implement them in a derived value object class. The compiler will notify us about that. Second, we are making sure that the object coming to the equals core method is of the same type as the current value object, and it is not null. Thus, we don't need to duplicate these checks in the derived classes, we can just gather them here. The equality and inequality operators are the same as in the entities. Now, let's look at how we can use this class. We can derive money from it, and you can see as soon as we introduced the inheritance, the compiler tells us that we need to implement the two abstract methods. So let's do that. For the equals score method, we need to check the equality for each of the properties. And the same goes for the getHashCode method. All members of the value object should take part in the hashcode generation.